we will use something called the octet rule, the tendency of many atoms to gain or lose electrons in the most direct way to get an 8-electron set corresponding to S2P6. That's the octet. And when most atoms bond, they will, the individual atoms will lose or gain or share electrons to get this filled S2P6 shell of electrons. There's something especially stable about that. Nature is telling us. So if we talked about the formation of lithium fluoride, we would know first lithium fluoride is without a doubt an ionic compound, because we know lithium is a metal and fluorine is a nonmetal. No doubt about that. So in terms of what happens to form the ions, we expect the metal to lose its one outer electron, valence electron here, to the nonmetal, which is one electron short of an S2P6 octet. Okay, so we would expect to see lithium end up as lithium plus with a 1s2 configuration, which is the helium configuration, which is quite stable, and fluoride ion, F minus, which is 1s2, 2s2, 2p6, which, hold your breath, I'm not sure whether this will work. Ah, it did, okay. 1s2, 2s2, 2p6 corresponds to neon. Okay. So we could represent the process of forming the ions by removing the least tightly held electron from the metal and putting it in the available valence spot for the nonmetal. This is not going to work for a noble gas because it doesn't have any spots. Right? Another way that you could represent this is with box diagrams. The box diagram clearly shows here's the 2s electron for lithium, and we can take that electron and imagine that it will be promoted up to the fluorine's 2p subshell right here. Now, that's not to say that that's easy. It's not easy, but that's how we picture it. Yes?
What if it has 4 valence electrons? Does it gain 4 or lose 4?
If you're talking about the formation of ions, it doesn't do either one. But if you're talking about covalent bonds, it shares 4.
You said it wants to be 8 electrons with the octet rule?
Yeah. The significance of the octet rule is that when the compound is formed, it either contains a central atom that has 8 electrons as 4 bonds, or 3 bonds in a lone pair, or something like that, or it contains ions that have that electron configuration. But there aren't any stable 4 negative or 4 positive ions, except for a few heavy metals that we talked about the other day. We have the rules for them. Well, there's an easier way. These are both sort of kludgy ways of doing things. We can use Lewis dots. And this is the first example of many that I'm going to show you where Lewis dots can A, save your bacon, B, save your time. If you do the Lewis dot diagram for lithium, there's 1 dot. For fluorine, there's 7 dots, 3 pairs and a single, and it's very easy to imagine the lithium electron going over and pairing up with the single electron of fluorine to make fluoride and lithium plus. So you can see that it's, if you could draw the Lewis dot diagrams, how much easier that is to imagine than this big box diagram or this electron configuration diagram up here. Questions on that? Okay. An example. Show the formation of sodium oxide, Na2O, with electron configuration, orbital diagrams, and Lewis dot symbols. All right, Na2O. So we take 1 oxygen atom, and 2 sodium atoms, and we look at their electron configuration according to these steps here, or approaches, if you will, and we try to make octets. So here are the 2 sodiums. The outermost electron configuration of sodium, or the valence, is 3s1. The oxygen is 1s2, 2s2, 2p4, so it has it's 2 electrons short of the neon configuration, right? So that's the reason why 2 sodiums are involved. The sodium, each sodium is the source of 1 electron. One of them goes here. And the other one goes here. So that we get an oxide ion. This becomes O2 minus. And the oxide ion is shown over here with a filled subshell, 2s subshell, and a filled 2p subshell. And you have 2 sodiums, each of which have the neon configuration. So everything, all of the ions, all 3 of them, have stable electron configuration. If you use the Lewis dot approach, then you've got oxygen with 2 pairs and 2 singles, 2 sodiums with 1 electron each. They can make their contribution of 1 electron to the oxygen each and make a stable octet configuration for oxide ion right here. And again, I suggest to you that that's a lot easier to conceive, than trying to do a box diagram or electron configuration case. Okay. Now there's some things about ionic compounds that you know, and you may know what I'm going to show you here. But in case you don't, here's a little movie of what happens when you take some metallic sodium and you drop it into chlorine. Chlorine gas is sort of a yellowish gas here. And there's a little sodium here, and I hope you'll be able to hear this. And what you should focus on is understanding why the delta H formation of sodium chloride is large and negative. Right? Meaning, when sodium chloride forms, a lot of heat is released. You don't believe it?
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
Clean off the surface. Instant replay. Okay, I'll tell you right now, the bottom of that flask is very hot. A lot of heat came out of that. So where's the heat come from? Yes? That one? Oh, must be this one. Thanks for telling me. I appreciate that. I didn't think about it. Okay, so where does the heat come from? First of all, write down on your paper the formation equation for sodium chloride. So the delta H of formation is minus 411 kilojoules, which is a big chunk of a megajoule. What is the equation for which that's delta H? Okay, it shouldn't take you too long to do that. the formation equation forms 1 mole of the compound in question, and in this case, sodium chloride comes as a solid, so it's 1 mole of sodium chloride solid. The formation equation then involves sodium in its elemental form and chlorine in its elemental form. That's what formation means here. So this would be Na, solid, plus chlorine comes as a diatomic, and we only need 1 mole of it, not 2 mole. So we're going to choose 1/2 Cl2 gas. And the delta H for this reaction is equal to the delta H of formation of sodium chloride. So that's what we saw. You saw the sodium, and I showed you the yellow color of the gas, the chlorine gas there. So the question is, why is this equation so exothermic? We have to think about that for a moment. And what I would like to propose to you is the following idea. There is a property of ionic compounds which does not have a parallel in covalent compounds, and it only plays a role in solids. It's called the lattice energy. The lattice energy is finally responsible for why that formation reaction of that solid was so exothermic. Okay, so I need to try to prove this to you. So the first thing I'm going to do is I'm going to take the first ionization energy of lithium. We're going to see what it is and what the magnitude of it is. The first ionization energy, of course, is lithium in the gas phase, 1 mole, making lithium ion in the gas phase, 1 mole, and giving a mole of electrons, and that costs 1/2 megajoule in a liter. So that's a very endothermic process. Now we'll take that electron that we got, and we will give it to the fluorine atom. And the energy change for that is the electron affinity. Okay, so 1 mole of F in the gas phase plus an electron goes to 1 mole of F minus, a fluoride ion in the gas phase, and the electron affinity is exothermic to 328 kilojoules. Now, if we add these two things together, we can add these are basically delta H values, so we can add those to see what the predicted energy change is for the combined two reactions. So this would be lithium gas plus fluorine gas goes to lithium ion in the gas phase plus fluoride ion in the gas phase, and the energy change is 520 minus 328, or it's plus 192 kilojoules. So can this be where the energy comes from? What do you think? Can it be? Is this energy released? It's not, is it? What would the sign have to be if this were energy released? It would have to be negative. It's not. It's positive. This process takes 192 kilojoules per mole. So that's not where the heat comes from. So we have to think some more. The endothermic electron transfer is clearly not favorable, but lithium fluoride forms even more violently than sodium chloride. The delta H of formation of solid lithium fluoride is negative 617 kilojoules per mole. So if you take 1 mole of lithium solid plus 1/2 mole of fluorine gas, and you form 1 mole of lithium fluoride solid, the delta H for this is equal to the delta H of formation of lithium chloride, which is negative 617 kilojoules. Now, the difference between the gas phase process, which was unfavorable, and the overall process here, which is quite favorable, has to do with the interaction of the positive and negative ions. And you all know that if you take a positive ion and a negative ion, and they're widely separated, the energy of interaction is what? Nothing, 0. right? Because Coulomb's law says the energy of interaction is equal to a constant times the product of the charges divided by the distance. Well, if the distance is halfway, is a large number, we'll say. I was going to say something about Pasadena there, but I take that back. A large number, then that makes the value of the energy very small. But in lithium fluoride solid, the separation is not large. It's tiny. These ions are not only very close together, but nature makes the structure in such a way that each ion, each positive ion, has 5 or 6 negative ions around it as nearest neighbors. So if the interaction in Coulomb's law between one lithium ion and one fluoride ion is, let's say, 100, then if there are 6 of those, that's 600 by itself. So solids arrange themselves in nature to maximize the Coulombic interaction and stabilize thereby the solid. So if we look at this, the lattice energy is that amount of energy which could be gained by taking a mole of separated lithium ions in the gas phase, a mole of also separated fluoride ions in the gas phase, and letting them come together conceptually and form a mole of lithium fluoride solid. That is where the Coulomb energy gets maximized. And that is called the lattice energy. Now, the lattice energy is a very influential parameter in the stability of ionic compounds. The lattice energy determines the melting point. It determines how hard the ionic solid is. And it has several other roles. How soluble the ionic compound is in water is partly due to the lattice energy. So it reflects the strength of ionic interactions. Now what I need to do is, I guess I've already said melting points and hardness here. I need to talk to you about how we can get a magnitude of the lattice energy. How can we determine this? Because this is not a process that you can carry out in a calorimeter and measure the heat. Okay? You simply can't do it. Conceptually, it's not feasible to even try it. So we have to have some indirect way to do it. And guess who gave us that? His name is Hess. Okay? The basis for indirectly measuring this process involves the use of Hess's law and a couple other nice thoughts. Okay? And in this process, we're going to show you something called a Born-Haber thermochemical cycle. It is one of the areas in midterm 3 that involves a calculation. There's one other, and that's all. So if you don't like calculations, take heart. There's only going to be 2, and this is one of them, and this is the more complicated of the 2. Okay, I want to show you pictures first. Let's take the formation reaction of lithium fluoride and show it on an enthalpy diagram. Right? Up here are the reactants, and down here is the product. This is lithium fluoride solid, and the picture shows lithium ions and fluoride ions in alternating positions with a lot of the ions of the opposite charge around. And of course, lithium solid is this stuff over here, a metallic structure, and fluorine comes as diatomic molecules. So these are the F2s right here. Now, what we're going to think about here is that this reaction produces an energy change, and in this case we'll call it an enthalpy change, and it's equal to the delta H of formation of lithium fluoride. That's delta H of formation of lithium fluoride right there. Now, we can measure that, but that's not the lattice energy, right? That is not the lattice energy. And Hess says but you can use it to get the lattice energy. Here's how it works. We're going to start at the same place that we did for this reaction, but we're going to go up. And we're going to take it step by step. And let me just add that if someone tells you that to solve one of these Born-Haber Cycle problems, all you have to do is add the numbers up, laugh in their face. It's not that way at all. You have to think about it. And you've got to draw the cycle. If you take that advice, you won't be getting any credit for that kind of problem in the next midterm. And I don't want that to happen to you. Got to think about it. So the first thing I'm going to do is I'm going to take the solid lithium and I'm going to sublime it, meaning I'm going to heat it until it goes into the gas phase as individual atoms. Sometimes this is called atomization, and therefore the length of this orange arrow right here is also called the delta H of atomization of lithium, and in some problems it'll be referred to as the delta H of sublimation of lithium. Now we have lithium atoms in the gas phase, but we still have fluorine molecules in the gas phase, and you can see the picture over here. The next thing I'm going to do is to break the fluorine molecules into fluorine atoms. As we'll see a little bit later in Chapter 9, that means breaking the bond. F2 molecule has a bond, a single covalent bond between the atoms. We're going to break that bond, and that requires the bond energy of F2. Now notice here that we're only using half a mole of F2 because we only need 1 mole of F. If we used a whole mole of F2, we'd get 2 moles of F over here. So we're going to use a half, and so the enthalpy change for this guy is 1/2 of Be, the bond energy of F2. And you can look that up in a table. Okay? The next step will be to take the lithium atom and ionize it. Remove an electron from the lithium atom to make the lithium ion. So this big long orange arrow here is the ionization energy 1 of the lithium atom, and you know where to go and look that up, right? It's in Chapter 8. All right, now we have lithium ion in the gas phase plus fluorine plus an electron that came from the lithium atom over here. Ion plus atom plus electron. What's going to happen next? The fluorine atom is going to get the electron. And when it combines with the fluorine atom, the addition of the electron will produce an energy change. What's that energy change called? How about you in the greenish shirt there? Tell us what the energy change is called when the electron is added to the fluorine. I'm not surprised. Anybody else? Can anyone else tell me what that energy change is called from Chapter 8? Electron affinity. Thank you. The electron affinity is what is needed here. So the next step goes fluorine plus the electron plus makes fluoride ion. So lithium ion and fluoride ion are now formed in this step. This was step number 4 in the cycle. And we're almost done. All we have to do then is take the 2 ions, let them come together, and the last step will be equal to what energy? The lattice energy. Thank you. The lattice energy. So this is step 5, and the magnitude of it is the lattice energy of lithium fluoride. So here's where Hess comes in. And Hess says, okay, both of these processes start at the same place and the end at the same place. This delta H of formation starts right here and ends right here. This series that makes up the rest of the cycle starts here, goes up, 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 down, 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 and stops right there. They both start at the same place and end at the same place. So what must be true, according to Hess, about their overall enthalpy change between the 2 of them? They're equal. Thank you. They are equal. They start at the same place and the end at the same place. Delta H is the same for each one. So we can write an equation. You write the cycle because you need it to write the equation. Okay, I'm going to strip this down now, and I'm going to show you numbers rather than pictures. Hess's law, both paths involve the same overall delta H, right? So this first one, of course, is the delta H of formation, and the delta H of formation will be equal to the sum of the delta H's in the rest of the cycle. In this case, it's 5 steps with different formulas. This is determined by the formula of what we're making. With different formulas, it might be more steps than that, but it's 5 steps here. And the first one, the formation, is negative 617 kilojoules, as we saw before. The heat of atomization of lithium, which is delta H1 right here, is plus 161 kilojoules. It's a relatively small part. The bond energy of F2 divided by 2 is this next one. Bond energy is 159 kilojoules per mole. We divide it by 2 because we have half a mole, and that's that term right there. The next step is just the ionization energy of lithium, a mole of lithium atoms. That's plus 520. We just saw that a minute ago. The electron affinity of lithium is negative 328. I thank the person who told me that that's what that step was. Here is the magnitude of it. The table is in Chapter 8. We don't expect you to memorize it, but we do expect you to be able to use it. So, and the last thing here, we don't know what that is. That's the lattice energy. That's why we've been doing all this work, why my hair falls out and grows every semester. Okay? So, here we are. Delta H of formation of lithium fluoride, the length of the black arrow, is equal to plus 161 plus 159 over 2 plus 520 minus 328 plus delta H of lattice. So I'm going to plug in the values for everything except delta H5. Here, I've just reproduced the thing here. I'm putting in 161 for delta H1, 159 over 2 for 2, and so forth. You saw that. And then I'm going to plug in the value for the lattice energy. Then I have one equation, one unknown. I'm home free. I'm going to solve for delta H. Here it is, negative 1,050 kilojoules per mole. And be careful with signs because lattice energies must always be negative. I've done one for you. I want to do another one with the goal of being sure that you know the steps. And here's how it works. Here are the simplified steps. You start with the formula of the compound that you're going to work with. In case of lithium fluoride, Li plus F minus. You write the formation reaction for it, and you should know everything you need to know about the formation reaction. From the formation reaction, you write the Born-Haber cycle and the equation which describes it, and then you solve it the way we did up here for the lattice energy. So let's suppose that we had a different kind of compound with an MX2 formula. Most students understand the steps in MX, like lithium fluoride or sodium chloride, but sometimes they get in trouble when they have to think about a different formula. Well, this formula, I think it goes without saying, involves magnesium 2 plus and 2 fluoride ions. So the lattice energy for this is the energy released when a mole of magnesium ions in the gas phase combines with 2 moles of fluoride ion in the gas phase to make 1 mole of magnesium fluoride crystals or solid. Okay? The formation equation is Mg solid plus F2 gas goes to MgF2 solid. So that's where we start with the Born-Haber cycle. And I have I've illustrated it over here. MgF2 is going to be Mg2 plus, and then F minus taken 2 times. Ultimately, what we want to solve for is the delta H of this process, Mg2 plus in the gas phase, 1 mole of it, plus 2 moles of F minus in the gas phase. And these things come together from the gas phase and form the solid. This is delta H of lattice. Okay? So what we need to do to make our cycle is to figure out how we can get from magnesium in the elemental form, magnesium solid, up to magnesium 2+, and diatomic fluorine to F- here, fluoride ion. That's what the essence of making the cycle is here. All right? So let's go through the steps, keeping in mind that the last thing that we have in the cycle before coming back around to complete the cycle has to be Mg2+ in the gas phase and 2F- in the gas phase. Everybody comfortable with that idea? Okay, so these are pieces of information that you might need. And typically when you see a problem that asks you to calculate a lattice energy, you'll see a whole bunch of information here. That doesn't necessarily mean you need to use all of it. It means it's available for you when you write the cycle for each step to pick out what you need. Okay? And if somebody, as I said last time, says, oh, those problems are easy, you just add up everything they give you, you should look with some skepticism on that advice. Okay. So the first thing we need to do is take the magnesium out of the solid to the gas. And here, incidentally, is the magnitude of the delta H of formation in the direct reaction. So I have set this up to take us from magnesium solid and F2 gas to magnesium gas and F2 gas. And what I require to do that is an amount of energy called the delta H of atomization of magnesium. Sometimes it's called the delta H of sublimation. Those two things are the same. So that means to get from this level, this is delta H increasing this way, from this level up to this level is that delta H is equal to plus 146 kilojoules per mole. Right up there it is. Okay, so that gets us to that point. The next step is to get from F2 to 2Fs. In other words, take the F2 molecule, break the bond in it, and make 2F atoms. And that requires the bond energy of F2, which is plus 159. So I'm going to write down here plus 159 kilojoules per mole for that step. Okay? Now I've got the atoms. I need to make the ions. Let's make the magnesium ion simply by removing an electron and then removing a second electron to get to Mg 2+. Okay? So the separation between this level and the top level here is equal to the sum of the first ionization of magnesium, plus 738, plus the second ionization for magnesium, which is plus 1451 kilojoules. So that will take a mole of magnesium atoms, and it will make a mole of magnesium ions plus 2 moles of electrons. Is that good? Everything comfortable there? Okay. Then the next step, we let these 2 electrons that came out of this process combine with the 2 fluorine atoms, and we get an energy change of 2 times the electron affinity of fluorine. So this is the next to the last step, and this is 2 times the electron affinity for fluorine is negative 328, so it's 2 times negative 328 kilojoules. Okay? And then finally, we have the magnesium ions plus the fluoride ions going to magnesium fluoride, as we said before. That's delta H of lattice, and that's what we're going to solve for. So we're going to set delta H of formation equal to the sum of 146 plus 159 plus 738 plus 1451 plus 2 times negative 38 plus the lattice energy, and we're going to solve for the lattice energy. That's what making the cycle means, and it is all dictated by the formula of the compound that we're making the cycle for. So Delta H formations at minus 1124. Then we have sublimation 146. The bond dissociation energy. Now notice we don't use half of it here. Why not? Before we used a half.
Because there's 2 moles.
The formula tells us we need 2 moles of F, fluoride in this case. So we get them from 1 full mole of the F2, and that bond energy is shown up here at 159. Then we have the 2 ionization energies of magnesium and the 2 electron affinities and delta H of lattice. And finally, we solve this thing, and we get almost 3,000 kilojoules per mole exothermic. Why do you suppose it's so much larger, more negative, than the 1,000 we got for lithium fluoride? Okay, what about periodic trends? What do we know about how lattice energy should, the magnitudes of the lattice energy for different ionic compounds? Well, we just showed lithium fluoride had negative 1,000 roughly, and magnesium fluoride had negative almost 3,000. So there's a trend that has to do with the charges on the ions. Okay? We can say in general that the magnitude of delta H of lattice, which is always negative, it's always negative. If the ions have opposite charges, it's always negative. It depends on the size of the ions, the charge of the ions, and the arrangement of ions in the solid. Now, in this course, we're not going to consider the third one. I'm not sure whether they will in 1332 or not. I doubt it. We will definitely look at the ionic charge effect and the ionic size effect. And of course, these will be based on Coulomb's law. And for the electrostatic energy of a cation A and an anion B, the electrostatic energy is proportional to the product of the charges divided by the distance between them, which is the sum of the radii of the ions. So this distance here is really R of the cation plus R of the anion. It's the sum of their radii. So we can rewrite this. The electrostatic energy is equal to the cation charge times the anion charge divided by the cation radius plus the anion radius. A little algebraic considerations here. Changes or increases in the cation and anion charge will have a bigger effect than changes in the radius because the charges are multiplied together, the radii are added together. So we'll look for that as time goes along here. So if we break these things down into individual effects, let's first look at the effect of different ion sizes if the charges don't change. We're going to compare 2 things that have different ion sizes but have the same charge, 2 m plus x minuses. And in general, since the distance is in the denominator of Coulomb's law, it's down in the bottom. If the distance gets larger, meaning the ions get larger, then if nothing else changes, the energy should decrease. Okay? So as the ions get larger, the energy of attraction decreases. And so does the lattice energy. So it would take, I've chosen 3 examples here for you. The lattice energy of sodium chloride is greater, that means more negative or more exothermic, than that of sodium bromide. The sodium is the same in both cases. The chloride is smaller than the bromide. So that means in sodium bromide expression, you'll have a larger denominator, which will make the lattice energy less negative. Okay? So that's the effect of the ion size. It causes D to be larger or smaller. If we look at cases where the radii are similar, but the charges are different, then you see the effect of the charges being multiplied together. If we look at magnesium chloride and sodium chloride, the chlorides are the same in both, and magnesium is a little bit smaller than sodium, but it's not enough difference to write a letter to the governor about. So if we look at this and we realize that the charges are multiplied together, a small difference in the radii is going to go out in the wash. Okay? So magnesium chloride with 2 positive charges and 2 pluses and 2 1 minuses is going to have a more exothermic lattice energy than sodium chloride, where we have 1 plus and 1 minus. If we take that another step and we look at magnesium oxide, magnesium oxide has 2 plus and 2 minus. So now that multiplying together is going to be a factor of 4, and that will have a lattice energy that is even more exothermic than magnesium chloride, where you have magnesium 2 plus and you have 2 chlorides, 1 minus. So that's how you can compare qualitatively the magnitudes of lattice energies just looking at the formula.